Hey y'all, today we're going to discuss polar and nonpolar bonds again. We talked about these a little bit last unit. But we're just going to expand on that a little bit and figure out how these Lewis dot structures and how these geometries can relate directly to something being polar or nonpolar. In review, we know that a polar bond is uneven sharing of electrons, and a nonpolar bond is going to be even sharing of electrons. Um, we know that this has to do with electronegativity. So with the electronegativity, we know some atoms like to take electrons from other atoms a lot more. And we can look at the periodic table to determine which atoms want to take electrons and which atoms want to continue holding on to their electrons versus which atoms like to lose electrons really easily. So we're gonna talk a little bit about the electronegativity of specific atoms as well. The final thing we're going to discuss, this is a new topic today, is a vector. A vector is just a force in a specific direction. So if you put your arms out to both directions, like this, and you have somebody on this side pulling your arm and somebody on this side pulling your arm's going to be pulled in these directions. And when they're getting pulled, we have these specific vectors, no more specific forces. So we can use vectors and forces to determine how a specific bond is going to look and how we can figure out if it's going to be a polar or a nonpolar bond. We have these 5 geometries. We're going to work through the 5 geometries we discussed in a previous video. Let's start with our molecule CO2. We've worked through CO2 a lot now. CO2 has carbon with 4 valence electrons. Oxygen has 6 valence electrons, and there are 2 oxygen molecules attached here. When we do this bond with our unpaired electrons, we find that we're going to have a double bond formed between our carbon and our oxygen. And that our carbon molecule is going to have 0 unpaired electrons around it, and it's also going to have 0 lone pairs of electrons around it. So if we break this down, we have 2 bonded atoms. We have 0 lone pairs. We have 2 electron domains. So this is going to be considered a linear molecule, if we remember correctly. Now, if we look at how this works and we pay attention to the periodic table, we know that oxygen has a higher electronegativity than carbon, right? It's stronger. It's farther to the right than carbon is, so it has a higher electronegativity. So what that means is the electrons are going to be pulled in this direction toward that oxygen. But we have 2 oxygens in this molecule. So we're also going to be having electrons pulled in that direction from our carbon. Remember, they're still sharing the electrons, so we aren't taking these electrons away like an ionic bond would, but we're having pulling in both directions of this carbon-oxygen bond. When we have pulling in both directions like this, we have to figure out how strong is the pulling. The bond between carbon and oxygen has the same electronegativity, as the bond between this carbon and oxygen because there's the same difference of electronegativity between oxygen and carbon. If we have equal pooling in both directions, then we have equal sharing of electrons. And this would be considered a nonpolar molecule. Those arrows represent our vectors. That's the force that's pulling the electrons away from the carbon because oxygen has a higher electronegativity. You're going to find that if you work out any linear molecule or almost any linear molecule, they're almost all nonpolar molecules. Another geometry we've discussed, and we'll work through the example BH3. It's an example we've been working through. We have boron with its 3 valence electrons, hydrogen each with their 1 valence electron. When we connect our dots, we can redraw our molecule, boron, with a connection to a hydrogen here, a connection to a hydrogen here, and a connection to a hydrogen here. If we're trying to figure out our geometry, we have 3 bonded atoms. We have 0 lone pairs around our boron molecule. We have 3 electron domains. So this would be considered a trigonal planar molecule. Now, if we want to discuss our vectors, boron has a stronger electronegativity than hydrogen. So the electrons are going to be pulled closer to boron. And we have 3 hydrogens all pulling these electrons this direction. Boron to hydrogen is the same on all of these chemical bonds, right? They are all boron to hydrogen. It's not boron to fluorine. It's just boron to hydrogen. And in this case, since they're all the exact same bond, they're all being pulled with the exact same force. And when we have the same force with the same vectors pulling in the same direction, then we have a nonpolar bond. Because these electrons are going to be shared evenly between the boron and all the hydrogens. You'll find generally that almost all trigonal planar molecules are considered nonpolar. Another example we've been working through pretty regularly is CH4, or methane, carbon tetrahydride. Carbon, we know, has the 4 valence electrons. Hydrogen each has 1 valence electron. When we do these chemical bonds or these connections between our valence electrons, we know we have a molecule where carbon is attached to hydrogen. As such, we have 4 bonded atoms. We have 0 lone pairs. So we have a total of 4 electron domains. When we have 4 bonded atoms, 0 lone pairs, and 4 electron domains, we have a tetrahedral molecule. If we draw our vectors on this molecule, carbon has a stronger electronegativity than hydrogen. So the electrons are going to be pulled toward carbon in this bond. In this one, it also has a higher electronegativity than hydrogen. This has a higher electronegativity than hydrogen. And this one does. If we observe the vectors in all of our bonds, we see that we have even bonds, and they're all being pulled toward the carbon. If they're all being pulled evenly, we have a nonpolar chemical bond. you'll find most of the time that your tetrahedral molecules are going to exhibit the character traits of a nonpolar bond. The fourth kind of molecule we've talked about, we've discussed H2O pretty regularly, or dihydrogen monoxide. H2O has an oxygen molecule, which has 6 valence electrons bonded to 2 hydrogen molecules, each with 1 valence electron. When we do these chemical bonds, we get a molecule of oxygen connected to hydrogen twice. And we have our lone pairs around our oxygen. This molecule has 2 bonded atoms. It has 2 lone pairs. So it has a total of 4 electron domains. When we have 2 bonded atoms, 2 lone pairs, and 4 electron domains, we have a bent molecule. Now this molecule is pretty tricky because we have 2 chemical bonds. They're both kind of in this area of the atom over here, right? There's no chemical bonds in this area. Those are where our lone pairs of electrons are. If we draw our vectors, we know that this bond is being pulled this direction and this bond is being pulled this direction. The lone pairs do not count as a vector. So imagine you have somebody pulling on, if this is you, and this is our chemical compound, this is you, and you have somebody pulling on this arm, and you have somebody pulling on your legs. As such, you're not being pulled evenly. There's nobody pulling you over here, so there's nobody pulling you from your head. So this is not even pulling. They're pulling from just 2 directions. And since they're pulling from 2 directions and not all directions, this is considered a polar molecule because it's not even pulling. We'll find almost all bent molecules are considered to be polar molecules because the electrons are not going to be shared evenly, and the force that's being pulling on those electrons is not coming from all directions. So most bent molecules you'll encounter are going to be polar molecules. The final kind of chemical compound or chemical geometry we've discussed, I think we use the example pH3, phosphorus with 5 valence electrons, hydrogen, each with 1 valence electron. When we do our chemical compound of our unpaired electrons, we're going to find we have a molecule of phosphorus bonded to 3 hydrogen molecules as such. We have 3 bonded atoms in this molecule. We have 1 lone pair. We have 4 electron domains. This is trigonal pyramidal. If we draw our vectors, our hydrogens are being pulled toward our phosphorus in 3 directions. There's no pulling at the top. So we would consider this uneven pulling or polar bonds. Most trigonal pyramidal molecules you will encounter are polar bonds. A general rule of thumb you can follow is if you have a symmetrical molecule, you have a nonpolar bond.